All right, welcome to the Explainer. Today we're going to put on our detective hats to solve a bit of a mathematical mystery. No, we're not at a crime scene. We're deep in the world of variables and equations, and our job is to uncover the truth.
So what is it that makes a math sentence a mystery in the first place? Well, just like in a good detective story, some statements are just open and shut facts, while others, they're full of questions, leaving the case wide open.
Okay, check this out. On the one hand, you have a statement like 2 plus 3 equals 5 plus 0. That's a closed case, right? It's a solid fact. It's always true. But then you get something like x plus 10 equals 14. Well, is it true? I don't know. It depends. The truth of that whole sentence hinges on the identity of that mysterious character, x.
And this is our central piece of evidence. This is the heart of the whole mystery. In algebra, we call it an open sentence, and it's really where our investigation begins.
So what we're really saying is, an open sentence is basically a puzzle with a key piece missing. The statement itself is kind of just floating there. It's not true, it's not false, not until we find the exact value that fits in there. It's like an unfinished story, just waiting for its last chapter. Now, every good mystery needs a person of interest, right? That central, unknown figure that the entire case just revolves around. Well, in the world of algebra, we call this the variable.
And here they are, the usual suspects. Could be an x, a y, an r, or an n. It doesn't really matter. This letter is just a placeholder for a number we haven't figured out yet. It is the who in our mathematical whodunit, and it's our job to unmask them.
But a good detective can't just go around randomly accusing people. They need a specific, credible list of suspects to investigate. In math, this official list is called the domain.
For the cases we're looking at today, this is our official lineup. The only suspects we are allowed to investigate are the numbers 0, 1, 2, 3, 4, and 5. That's it. If there's a culprit, they have to be on this list.
Okay, now this is where the real detective work kicks in. It's time to interrogate our suspects. We're going to test each value from our domain and see whose story holds up. Let's start with case number 1. The case file is open. n plus 3 equals 7. We are looking for that one single number from our lineup that can take the place of n and make this whole thing true. Time to start the questioning.
You can see this process is just like an interrogation. We bring in suspect number 3. Does 3 plus 3 equal 7? Nope. Verdict, false. Their alibi checks out. Next up, suspect 4. Does 4 plus 3 equal 7? Yes! Verdict, true. We got a confession. And just to be thorough, we check number 5. But nope, their story doesn't check out either.
And boom, there we have it. The only value from our entire list of suspects that makes the open sentence true is 4. We've identified our culprit. Case closed. Okay, but let's be real, not all cases are that simple. Sometimes it's not a lone wolf. You're dealing with a conspiracy. Let's look at a new case, this time an inequality. n is greater than 2.
So we run the same exact procedure, interrogating each suspect from our lineup. Is 2 greater than 2? False. Okay. Is 3 greater than 2?
True.
How about 4? Also true. And 5?
True again.
Well, would you look at that? It seems we have multiple accomplices.
And there you have it. The full story is that suspects 3, 4, and 5 were all in on this mathematical caper. Our solution isn't just one number this time, but a whole set of them.
Get ready for a total plot twist here. This is like that classic Murder on the Orient Express scenario, where the evidence seems to fit everyone. The open sentence is x minus x equals 0. So let's run the interrogations. If x is 0, we get 0 minus 0, which is 0. True. What if x is 1? We get 1 minus 1 equals 0. Also true. What if x is 2? Yeah, you see the pattern here, right? In this bizarre case, every single suspect from our lineup is guilty.
But what about the flip side of that? The really frustrating cases where you have a crime. You have your list of suspects. But after all that work, nobody's story fits the evidence.
We bring in every single suspect, one by one, and test them against the equation 2 times m equals 7. But this time, every single interrogation comes up empty. The verdict is always false. No one confesses, because in our lineup, no one's guilty.
And that, my friends, is what happens when a case goes cold. Sometimes the solution just doesn't exist within our specific list of suspects.
In mathematical terms, we say the solution set is empty, and we represent it with this symbol here.
So all of this brings us to the final part of any investigation, filing the official report. This report, the one that lists all the culprits we've identified, is known as the solution set. The solution set is basically our grand conclusion. It's the definitive, final list of every value from our lineup that successfully cracked the case by turning that open sentence into a true statement. It might have one member, many members, all of them, or, as we saw, even no members at all.
So there you have it, the Math Detective's method. It's a clear 5-step process for cracking any of these cases. First, you identify the mystery. That's the open sentence. Then, you find the unknown, your variable. Third, review the suspects. That's your domain. Fourth, you interrogate them, test the values. And finally, you uncover the truth, the solution set.
So we've seen today how solving an open sentence is a lot like being a detective. But every single investigation we did today relied on a small, finite list of suspects. And that leaves us with one final really interesting question to think about. How would your methods have to change if your domain, your list of suspects, was infinite? What if you had to investigate every number imaginable?